Okay, well, thank you and good afternoon, everybody. I know that I'm the last person between you and cocktails, so I promise not to take too long. Just a little bit word about myself and my company. GQI stands for Global Quantum Intelligence. We're the leading business intelligence organization, supplies data and reports to the quantum industry. I myself started the Quantum Computing Report. You may know that. And I will be celebrating a 10-year anniversary for the Quantum Computing Report next few months. So we've been at this a long time, and we have a team of a lot of over a dozen people who understand quantum really well. So one of the things I wanted to talk about is a project that we've been working on at GQI to categorize and identify the most promising use cases of quantum technology to find a quantum advantage. You know, there's a lot of lists of use cases, but what we don't have is a really identification of which use cases are the most promising. And promising means the ability to do better than a classical solution. It means a large market. It means that it's not limited by other things. So I'm going to talk for the rest of this talk about what we're doing there. A lot of it has to do with classifying. So it's a project we're working on right now. It's not fully complete, but we will make it available for our clients. But we're going through 5 specific steps in order to do this and have this list of promising use cases. We are working, doing a literature search of all the technical papers and the commercial descriptions of use cases that have been identified. But then we're going through a fairly detailed classification of the use cases to classify them by the problem area, by what algorithm they're using, what the potential is for speed up, whether or not, how close they are to deployment, the size of the performance level of the quantum computer that needs to be, you need to have to run that use case, as well as the market size. And we're also looking at how it would compete against a classical solution. Almost all these use cases would have a possible alternative to perform it classically, but the classical solution may take very, very long, or may take a long time, or it may not be quite accurate, or whatever. We have, as part of our tools, a resource estimation tool, and I'll talk about that in a few slides. What size of quantum computer you need, and we have a quantum market model that estimates the size of the market. So this shows sort of where we are today with some identification of the use cases. This is part of our data portal, where we put all the information in a database and we can display it with a visual tool. And I guess this works. And we have various ways of programming this. As a user, you can program it. You can filter it by country or organization, what industry it is, the problem domain. And so this is a very dynamic type of chart. And to give you an example, some of the things we can show, this shows the use cases with a color code. It shows it by the industry, and it shows it by the deployment status here. We have a graph that shows by country that it's in. These are actually some of the individual use cases. Again, we have a couple hundred use cases here. This just shows one. You can scroll down through this. And then you can also look at various approaches. I'll show you another screen that shows you an alternative view here. This is a chart, for example, here that shows what we call the classification, how we classify, whether it's an optimization or whether it's a simulation, and how that maps, how the use cases map, the number of use cases map to the various industries. We also collect what type of quantum computer it's used, whether it's a NISQ level computer, whether it's a fault tolerant computer, as well as sort of the type of computer, if it's trapped ion or superconducting or whatever. So we have a dynamic display, and if you want to catch me either later today or tomorrow, I can give you more, I can show you this in real time. So as part of our classification, besides all these things, one of the things that people are very interested in is understanding, of course, what industry it's in, what type of computational science it's in, and as well as the algorithm. So, we're developing this for one of our clients who has a sales force, a business development force, and they will call on a customer, and they'll want to know, if they talk to like a bank, what type of use cases has GQI identified that might be applicable to a bank. So that's what's shown here in yellow. Obviously, the industry vertical is shown here. This would be just examples of the specific problem, and then the use case, what that might be in terms of more details. The business development person might talk to the technical people, and they want to know a little bit more about what computational area is it in. Is it computational chemistry? Is it optimization? Is it numerical modeling? Those types of things. And again, more detailed, they might want to know if it's a factoring problem, or if it's a traveling salesman problem, or a fluid dynamics problem, and that type of thing. And so we're labeling all of these use cases that we're finding by this, as well as this third element, which again goes more deeply into the quantum thing. What algorithm does it use? Does it use Shor's algorithm? Does it use variable quantum eigensolvers? Does it use annealing? And again, we have it down to a more primitive level. So, one of the basis of Shor's algorithm, for example, is quantum Fourier transform. So we have that listed, and that's entered into the database. And then we have placeholders here, but if there's a technical paper that describes that, we will also have that in our database. So beyond that, though, there are certain things that you want to understand about a use case. We've categorized it, but we don't want to really know if it's a practical, because some academics will write a paper on a use cases, how they solved a certain problem, but is it realistic, or is it valuable in what we would call the real world? So we have this thing called a quantum decision tree to help drive the technical assessment. And there are certain things that we would look at to understand whether this is really practical to use. There are a lot of use cases, for example, where, you can do something quantum, but the key bottleneck is not in the computation itself. It could be in the I/O, as we show here. It could be limited by I/O. It could be something, if it might be quantum sensing, we would have a different program for our customers on quantum sensing, or is it a quantum network? So you want to make sure that it's something where computational performance, in this particular project, it's computational performance that's important. And we also want to know the type of algorithm. Some algorithms are algorithms that we have been able to characterize. Some algorithms are what we call heuristics. We just know that it seems to work, but we may not have a theoretical underpinning of exactly how it works. The next thing to understand is the speed up potential. This is very, very important. Quantum algorithms are typically characterized by how they scale. As you increase the number of parameters in the problem, Will the time to compute go up by a polynomial? Will it be exponential? Will it be super polynomial? And those types of things. One of the things that most people believe, most of the experts believe, is that if you have a quantum problem that only has quadratic level speedup, at the end of the day, you're probably not going to find it valuable. And the reason for that is because the quantum gates themselves are much, much slower than a classical gate. And it's just not large enough to really give you an advantage in a thing. What you're really looking for is either super quadratic or super polynomial or exponential type of speed up. So we will analyze that type of thing. Again, I'll show you some stuff. But there are some quantum annealing, for example, is an example where many algorithms or quantum VQE, for example, they're more heuristic. You have to sort of try it out to know if it works or not. So we will explore those, and if we're able to do that, we'll do a resource estimation and be able to figure out what the computational time is and how many gates it is. And that maps into another framework we have. We do divide the quantum development into different time frames. And the time frame is measured by this measure called QOP, Q-U-O-P. That stands for quantum operations. So today we're in the NISQ area, and maybe you can do a few thousand quantum operations before the error rates get too high. As we've seen all day today, we're moving pretty rapidly into what we call the mega QOP era, where we'd be able to do 1 million operations. And then beyond that, there's the teraQOP and more. So there may be a good use case out there, but you won't have the computers available to process it until maybe 5 or 10 years from now. So those are things that our clients want to know about, and we do those analyses. And as part of this, we do a resource estimation. We are able to take an algorithm, and in many cases, we can program different parameters. If it's an ion trap machine, we'll have a certain set of parameters. You can see some, go back here for a second. You can see some of the parameters there. We have models for superconducting systems, models for ion trap systems, models for Majorana systems, with various levels of fidelities, gate level fidelities. And this is an analysis we did. You can actually read about this in the Quantum Computing Report. We have a couple of articles that show this and describe it in more detail. But each one of these little things is a different algorithm, but you can see that it covers a space. Each one of these points here is a different machine configuration. Again, there are 2 machine configurations for superconducting, 2 machine configurations for ion traps, 2 for Majoranas. So we have, in this chart, we have something like, I don't know, 8 or 9 different things, but we have a lot more estimates in our database. So to give you an example of some of the things, again, this is still, the last thing we do is do a quantum market model. I think you've heard today that people are estimating that quantum may ultimately be a trillion dollar market. GQI has its own market model. And the thing I'd like to point out is, yeah, the trillion number is there, but first of all, it's 2050. I think I'll be retired by then, not sure. But that is actually comprised of 2 different components. The first component is the revenue that the quantum providers would get. And we have separated that by what we call the value chain elements. The people who are supplying the components, the people who are supplying the computers, the software, those types of things. And that's sort of this bottom level here. And then there's a second portion of value, which is the value that the end users are going to get. If you are a drug company and you develop a new drug and you, using quantum computing, and you are able to you are able to sell $100 million worth of that drug, that's value. It doesn't go to the quantum providers, but it goes to the end users. Alternatively, if you're a manufacturing, let's say you have a manufacturing plant, and you're able to improve the efficiency of your manufacturing plant, let's say by 20% or 25%, by implementing a process flow which is more efficient because you've simulated it with quantum computing, that would also be part of the value there. So our model incorporates both of those elements, both the end users and the providers, and what the value is there. And then to wrap up, we show, this is sort of a summary. And again, it's an initial summary. What we have done is shown the value, the various use cases for 9 different industries. And we have a very sophisticated bubble chart here. This shows the scale of the quantum computer that's needed, as I talked before. This shows the potential economic impact. You can see, for example, that we do predict that drug discovery is going to be a major use case, but it's also going to require a large-scale quantum computer, a fault-tolerant quantum computer. We have also the size of those circles represents the scalability potential. What the competitive advantage versus classical is shown by these charts, and you can see these semicircles around here. So that means it has some competitive analysis. If it's a full circle, then it would be very high, as well as the integration complexity. So we've done that for, just to show you again, financial services, pharmaceutical and life sciences, healthcare and medical devices, cybersecurity, defense, telecommunications, all the various use cases there, the energy industry and oil and gas, for automotive and aerospace, for those industries, what some of those use cases are, advanced manufacturing, what are the use cases and what are the use cases there? So, and chemical and materials, use cases for those. And one other thing is we have divided these into, to show you, these little icons here. A lock means for cryptanalysis. This thing, I don't know what you would call it, is for simulation. And you can see those here. So the little test tube there, for example, is for biochemistry detection in this particular case. Oh, and finally, logistics and supply chain, vehicle routing, warehouse layouts, those types of things. Oh, agriculture and food production, we have another set of use cases for them too. And environmental science and climate change. I think there's 9 industries, maybe there's more. I haven't counted. Anyway, so that's sort of our what we've been working on. It's an ongoing project at GQI. It's really intended for use for our clients to really focus their business development efforts with regard to understanding the use cases, which use cases are the most promising, and help us all reach quantum advantage earlier. So with that, that's all I have. I don't know if there are any questions. I guess there's no more questions. So thank you for your time, and I think it's cocktail time. Thank you.